Let's continue with the chapter. This is, as I mentioned, analysis of algorithms. And to the end of the chapter, we will discuss some properties of trees. So why do we need to analyze algorithms? So we have many algorithms. In this course, we are going to discuss some algorithms related with computer-aided design, related with computational geometry, and some will have poor performance, some of them will have a better performance. So how do we understand if one algorithm or if one program is better than the other? So that's why actually in order to find an answer to this question, we have some kind of a method. In a moment, we will discuss this method. And with the help of this method, we can easily conclude whether the given assignment, given program is a better one or not. First of all, what is an algorithm? It's a generic step-by-step list of instructions. So in the algorithm, you cannot have a single instruction. You should have many instructions. Sometimes, as you know, you may have some loops depending on the problem you're solving. But the thing is that your algorithm should be solving a problem. This is a must. On the other hand, the program, actually, the scripts you are writing based on the given algorithm are actually some kind of coding, some coded scripts, and you can use any programming language. So you may have a single algorithm, but many types of programs using the same algorithm. Since they may be using different languages, their implementation style might be different, they may be using different classes, but still they might be using the same algorithm. Yes, that's it actually. You may have many programs for the same algorithm. So let's have a look at this example. What is it doing is summing the numbers actually up to n. So the name of the function is sum of n, as you see. Initially, the variable, the sum is equal to 0 right now. But once we have a for loop here, it starts summing the numbers starting from 1. And it will do the summation operation until it reaches the last number, which is n here. So if I write it here, this is something, let's say, oops, did not, yes. So it will be doing such a summation plus n. So this is what it is doing. And if you look at the bottom one, we have different names, but it's the same. Just the name of the variables are changed, but the algorithm, the code, the script is exactly the same. So we cannot comment on which one is better. They are exactly the same, so their performance is the same, and we cannot say anything about the performance of, about the comparison between the performance of these two implementations. So that's why actually it's quite difficult to do an analysis, do a comparison by just looking at the script you have written. So it's better we have a formal actually analysis, and these analyses should depend not on the competing resources you have or not on the type of programming language you are using. So you should find an independent way of comparing these algorithms. And sometimes if you cannot find the proper way, you may also do a kind of a benchmark analysis, try to compute the amount of time actually is required for the computation of your algorithm. Yes, it's simply tracking the time. You track the time from the start of the algorithm until all the computation is executed. Yes, here we have the same example, but this time we have a kind of a benchmark. Here, as you see, we have two extra comments. This is a start variable. is equal to the time right now. Time.time, it will check the time and store it as the start time. And at the end of the operations, we have another variable called end. And it's again calling the time. It's stored as end. And once after every expression, every statement is completed, you return the summation and also the difference between these two time values. And that will give us the computation time for this algorithm. And here you see an example. It's summing actually the numbers between 1 to 5. It will do the operation for 5 times, and it's summing the numbers up to 20,000. So what is the sum? The sum is, as you see, we have a very large number, some 200 million, I think, yes, 200 million. The summation is obviously it should be the same for the 5 rounds, since we are summing the same numbers. But if you look at the time, they are almost the same. There are little differences, and these differences are just due to the operating system. In some of them, your operating system might be doing another task, so there are such little differences. And as you see, it's less than 1 millisecond, around 1 millisecond. You can run this script on your computer and observe some similar results. What about this one? This time we are not summing the numbers up to 20,000, but we have one more zero, so we are summing numbers up to 200,000. So the summation is more. And also, if you look at the time spent, it's this time around 14 milliseconds. The previous one, the computation time was around 1 millisecond, but right now it's around 14 milliseconds, and it's usually about 10 times the computation time of the previous one. As you see, this is 0013 somehow, and this is 013 or 14. So we have actually multiplied the computation time by 10, and as you see that the given number is also multiplied by 10. So we can say that easily there's a kind of a linear relationship between the number of inputs and the computation time. So the relation is, we will later discuss that this algorithm or this implementation has a time complexity of ON, or linear time complexity, since if you increase the number of actually inputs by 10, then your computation time will also be increased by 10 times. So we have this linear relationship, and we can say that this script has a linear time complexity. So here's a question: what is the variable inserting? This is inserting the summation. This is not complete. We have actually, this is complete actually is representing the summation of these values. So this might be not fully correct. I should check it, but we need to have two variables, obviously. And it's the output of this one is first the sum. So the sum comes here, %d, and then the time value comes here. So I think it should be fine. Any other questions, guys, before things are getting complicated? Okay, so do we have another actually way of computing the summation? Obviously, yes. If you look at this simple expression, simple equation, again, it's doing the same thing. This part is actually equal to just starting from 0 plus 1 plus 2 And as you see, it goes to n. So this is equal to the simple expression here. So what about using this one instead of having a kind of a for loop in our computation? So if you look at the initial implementation here, we did have a for loop here, and actually it was the main reason why we had a linear relationship between the number of inputs and the amount of computation, the time we need to have for the computation. But now, as you see, we will have a simple expression, and which means that we don't need to use a for loop. By using this simple expression, we can compute the same summation once again. As you see, right now, we have decreased the number of statements by just having a single statement. We can calculate the summation. And it's exactly the same. It will output the same value with the previous implementation. So you can give many inputs and try to check the computation time. That's it actually. If the input is 20,000, this is the computation time, and as you see, it's much less than the previous implementation. In the previous one, we spent almost 1 millisecond for 20,000, but right now we are just spending 1 nanoseconds. And if you look at the other values, even though we increase the number of inputs or increase the value of our n variable here, the computation time almost doesn't change. So it's almost the same. And these are, again, there are little differences, and these differences are due to your operating system. Probably it's doing some other critical tasks, some tasks based on your operating system. And we can say that regardless of the input, the computation time will be the same. So you can say that it's constant in time. Constant in time, we can compute this value, regardless of the value. Whether it's just 20, whether it's 2 million, 20 million, it doesn't matter. It will always spend the same time. Any questions, guys? So obviously, if we compare these two implementations, we can say that the iterative scripts will always do more work. So it's better you always, as possible as don't use any iterative solutions, but sometimes it becomes inevitable and we need to use iterative solutions. So obviously, for the iterative ones, the time required will be increased as your input value increases. So this is an obvious thing. And another issue is that, for instance, these were the values for my computer, but if you run this same script on your computer, probably you will get different values. So it will be, if you don't have an, let's say, independent analysis method, then it will be quite difficult to compare the performance of your algorithms. And again, the benchmark will not give, this is actually the benchmark we have done, it will not give correct results, and it's not a useful measurement. We need to find an independent method, which is independent of the processing power you have, independent of the programming language, and independent of the number of libraries, actually statements you are using. And that is actually called big O notation, or this is always coming from order. We will consider the order of operations in the script and try to come up with a simple, let's say, conclusion. We'll simply conclude that the given expression, the given algorithm is constant in time, linear in time, quadratic in time, logarithmic in time. So there are many types of complexities, and in this hour we will try to go over them and have some examples. So we need to have kind of an actually basic unit of computation, and that computation will be based on the inputs you are giving to the algorithm. And after you decide on this basic unit, in our examples it was n, then we'll try to simplify the expression and try to check how many n unit of operation will be performed in this algorithm. So once we have this information, then we can conclude on the time complexity. So if you consider our summation example, what we were doing, we were simply summing the numbers one by one. Once we were using a for loop, but once you use a simple equation, we just had a single statement. So in the for loop case, we had an initial assignment. So this is counting as 1. And then we have n number of summation operations. So this is actually the sum of operations we are performing in this implementation once you have a for loop. And obviously, n will be the size of our problem. So as n increases, then the time needed, time required for the computation will also increase. Any questions, guys? So what we are going to do, we will show how our algorithm execution time is changing with respect to the size of our problem. And sometimes we will have more complicated, let's say, T of n's. In this summation example, it was a very simple expression, but you will see in a moment that we might have such expressions. Let's say a plus b n plus c n squared, sometimes c cubed. So there might be such complicated implementations, and oops, this should be obvious n. I'm sorry. The thing is that at some point we will need to consider the highest order, and if this is your expression, then your time complexity will depend on this last term, since it will overpower the rest of these operations, and they will not be important. So this is actually what we are going to do in a moment. So we will always be using the dominant term for the comparison, but the rest will be ignored for our simplicity, and that will give us actually the value which is growing the fastest. And we will say call this one as big O notation, and as I mentioned at the beginning, O is for the order. So, and it will be written as O of f of n. So if f of n is n squared, then we will say that is O of n squared, and it has a quadratic time complexity. So this will give us actually the most dominant part, as I mentioned here. F of n is always the most dominant part of this T of n function. And by using the implementation, you can easily write the T of n, and then f of n will be equal to the most powerful part of your T of n function. So let's go back to the summation example we just performed. T of n is already written, 1 plus n. So what is f of n here? Since this is not important, our most important term is n. So I will say that f of n is equal to n. So that's why the big O notation will be equal to O of n. This is another example, for instance. We haven't written the implementation, but it doesn't matter. In this implementation, we see that there are some about 1000 constant operations. We have a special loop, a single loop running 27 times. And then we have two loops inside each other. We will see in a moment that once you want to have an n squared time complexity, then that means you should have nested loops. Otherwise, if you have a single loop, then it will be order 1. So if this is the T of n function, then f of n function will obviously be this part, n squared So I can say that it has an O of n squared, which means that its time complexity is quadratic. And in some cases, this is not actually a common way, but sometimes it might be quite complicated to determine this T of f function. And in such cases, we can determine the best case, the worst, and the average case, and try to give an average time complexity of the algorithm. Any questions, guys, up to now? I will now go through some frequently actually used functions in the big O notation, and we'll later then discuss some different types of time complexities. So these are some typical functions we need to use in the time complexity analysis. The first one is floor. What is floor? I think most of you are aware of it. For instance, if x is equal to, let's say, 5.99, what will be the floor function, the result of the floor function? Oops, this shouldn't be actually. Then the floor function will be equal to just 5. We are considering the integer, the largest integer, which is not greater than x. And for the sailing, if x is equal to, let's say, 5.0.1, then it will be the smallest integer, not smaller than x. So it will be 6. And then we have natural algorithm. You already know it. We have an exponential base here. And then we have binary algorithm this time. The base is 2. And we will be using them a lot in our analysis algorithms. Make sure that you are comfortable with them. Sometimes we may have an integer binary algorithm, and it will give us actually the number of bits in the binary representation of the given number. So if you want to determine how many bits are required to represent the value n, then you should take this logarithm, which also has a kind of an floor function embedded. It will give you the number of bits to represent the number n minus 1. So once you get it, you can sum it 1 and get the number of bits required to represent this number in binary form. Then we have two more, the harmonic numbers, hn. If you see that, then this is actually the expression it's referring to. It's summing these rational numbers, and at the end, you should have the last term as 1 over n. Then we have the factorial. It's the multiplication of the numbers up to n. We are starting obviously with 1. We have more of them. This is harmonic sum. The one actually we have just discussed is almost equal to natural logarithm of n. As you see here, it's almost equal to this value. You don't need to sum these together, so you can assume that this is it. A triangular sum actually we just discussed a moment ago in the example. Here we have an approximation, since if you don't want to have an approximation, then it will be exactly equal to n times n plus 1, right? Over 2. But since these will be large numbers, it's assuming that these two are equal to each other, and just simply take the square of n. And that's why we have an approximation sign here. And then we have a geometric sum. It's actually summing, as you see, the orders of 2, and it's equal to 2n minus 1, and it's approximately equal to 2 times the value of n. And it's only valid if n is equal to 2 to the power of n. And we have another equation, Stirling's approximation this time, and we are actually multiplying logarithm of n. This is the factorial of logarithm n. As you see, multiplication becomes summation if you distribute the items. So it will be the summation of these logarithms. And then we have binomial coefficients. In some algorithms, we will be using them a lot. So again, make sure that you are comfortable with the binomial coefficients. And it's approximately equal to n to the power of k divided by k factorial. And obviously, this approximation is valid once k is a very small constant. And lastly, we have an exponential function here. You can calculate 1 over e approximately by using such an expression, 1 minus 1 over x to the power of x. And as I mentioned, we will be using all these functions in the algorithms we are going to discuss in this semester. So now I want to continue with some time complexities. We have seen some examples. If you remember the second implementation of the summation example, we had a single equation, single expression. With the help of it, we did manage to determine the summation. So in such cases, if you have such expressions which does not depend on the value of your input, then you can say that the time complexity of your implementation is constant. Then we have another time complexity, and this is called logarithmic time complexity. Log of n, obviously, you will see that sometimes your time complexity will be not increasing linearly, but it's increasing logarithmically. So this is a bit better time complexity, and this is called as logarithmic time complexity, and we will see an example about it. And the most popular example is binary search. And these implementations, these in logarithmic time complexities, you should always be dividing your regions into halves. Otherwise, you cannot mention about logarithmic time complexity. Then we have the linear time complexity. This is not a difficult one. It's a very straightforward one. If your actually number of computations depends on the number of input, then that means probably you have a kind of a loop, you have a single loop, and we can say that it has a linear time complexity. So as you see here, n is our input, and this for loop will run actually for n times. So I can say that the amount of computation time depends on the number of input, depends on the size of the input. So there's a linear relationship, and the time complexity of that implementation is linear. For instance, here is an example finding the maximum value, this example. And generally, once you see a kind of a loop, you can easily comment that the implementation is linear in time. And then we have the multiplication of these two. This is called as linearistic, or sometimes it's called as log linear time complexity. And we have a specific example. It's quite actually difficult to implement such algorithms. And we have a famous example for it, divide and conquer. We will see an example in the upcoming slides, the merge and sort example. We will divide actually the regions into half first, and then do some computation. We will be actually sorting the numbers from the lowest number to the highest number, and then try to join them together. So since we are dividing the regions into halves first, and then doing some computation, that's why we have the multiplication of the logarithmic time complexity and linear time complexity. And we can describe it as divide and conquer. So you are dividing the whole region into smaller parts, and then doing some operations inside each region, and finally combine all these results. So now we will see the details of the logarithmic time complexity, the binary search. But we have a question in the second example. I think we in squares and concepts are not representation. I already explained. I think do you have any more questions? You may unmute yourself and ask it directly.
Yok hocam, sağ olun.
I couldn't hear.
Sorun yok hocam, sağ olun.
Okay.
Duyuyor musunuz?
So now we will discuss the basics of binary search, how we can implement an algorithm in logarithmic time. So we have actually in this binary search, we need to have a list, and this list should be actually sorted, and then we need to have a kind of a value, the value we are looking for, and then later what we are going to do, we will find the index of this key. In the previous lecture, we discussed some search methods somehow similar to them. And let's have a look at, for instance, this example. We have an ordered list. This is ordered or sorted. The smallest value is 6. And as you see, it's increasing. It comes to up to 97. And the number we are looking for is 33. So obviously we can say that by without doing any implementation, very simple one. 33 is here, so the index, the output will be 4. But how we are going to do it? By using some computational sources, and we want to implement a binary search algorithm. And we said that in such algorithms, we need to divide the regions actually into halves, and then try to work on these smaller regions and find this value in a shorter time. So how we start, we know that this is the start of the list, end of the list, and this is the middle of the list. This is 7, the 7th item here. Oops. Yes. So how we're going to do, we will be using just the left-hand side, the first half of the list. This part is here. We're not going to use it. And now we will check whether our given value 33 is in between the lower and the higher values. For the lower one, we have 6. For the higher one is 51. So I can easily say that 33 should be in between these two values. Then what I do, I need to divide it again into halves. And this time, I see that it's not only inside the left-hand side, but this time it's in the right-hand side. So I will continue. This is the lower part, lower index, higher index, medium index, and I can see that it should be in the lower region. And I do another, let's say, division into two halves. And lastly, I see that this time the lower part and the higher part is exactly the same. So I can say that now the value is found, and I can simply return index 4 as the output of my function or implementation. And we call these type of actually complexities as logarithmic, since, as I mentioned, we are always dividing into two halves. And then later checking whether our value is on the left-hand side or right-hand side. Any questions, guys?
Hocam bir daha anlatma şansınız var mı?
Sorry, guys, I have a problem with my speaker, so I will fix it and then ask you once you repeat your question. Just a moment. I think it will not be easy to solve it right now. Could you please write your question instead of speaking? So this is the implementation in Python. The function is called as binary search, and we have list actually as the input and the item we are looking for. So the last part, do you mean here actually? Yes, then let's start from scratch. We have the list, we have many numbers, and we are looking for the index of the number 33. So the function actually should tell us the index of the key, whether if the number is existing in our list. If the number is not there, obviously it will not output anything, and it will tell us that the number is not here. So what we are doing in the binary search, we are dividing the whole region into two halves. The lower part, upper part, and we have some middle value obviously. And then what we do, we check whether 33 is in between these values here or is in between the values on the left hand side. And obviously it's in between numbers 6 and 51. So I continue doing the same operation. It's between 6 and 51. So I continue dividing this region into half once again. And I see that it's not in between right now, this part. And so sometimes, obviously, if you cannot find the middle value, then you may assign it as to the left-hand side. It's not a big problem. So we see that on the left-hand side, we don't have value 33, but it's on the right-hand side. So I continue with the right-hand side and divide it again into 2. At this time, this is the left part, this is the right part, and I see that it's on the left part. And if I try to continue one more step, I cannot do that since I just have a single item left, and this time the left part and the right part are exactly equal to each other. So we can say that the algorithm is over. We can stop right now and return the value of 4. Yes, one of your friends pointed out it's similar to bisection method. Yes, you're right. And this is called as binary search. This is the implementation, the Python implementation. So the inputs to our definition is a list and item. So what we do initially, we have some assignments. We have a value first, which is equal to 0. And the last item, actually these two are lower and higher indices. So initially lower is equal to an index of 0, and higher or the last is equal to an index of the length of the list minus 1. Since once you call the length function, for our example, it will return a value of 15, but the index is 14. So that's why we have a subtraction here, minus 1. And then we have an output, which is found. Right now is false, which means that we haven't found the value yet. So it is assigned as a false value at the beginning of the loop. So then here comes our loop. So what we do actually here is doing the similar things we mentioned in the previous slide. It's dividing the region into half and then checking the number. Let's have a look at it. So what is doing? If first the value of lower index is lower or equal to the last, and if the number is still not found, we continue these operations. So what we do? First, we want to determine the midpoint, the middle index here. This is done with division, and we don't want to have any remainders, so that's why we use double slashes here. We sum the indices of the first and the last values. This will give us the index of the middle point. And then what we do, we check the middle point. So this is our input list. So once you write midpoint here, it will give us, for instance, if you're at this point, 3 will be your midpoint. And once you put it into your list, it will return 25. So the output of this part is 25. Is 25 equal to item? So if it's right, then you will say that it's true, and you don't need to do any other computation, and you can simply return that the value is inside the list, and you may further return the index of that item. But if it's not equal to that middle value, then what we do? We try to actually assign new lower or higher values. So if you look at here, for instance, we checked the middle value 33 is not equal to 25, and I have seen that 33 is on the right hand side of the region. So that's why in the next loop we are gonna focus on the right hand side, not on the left hand side. This is actually what is being done here. The last and the first indices are modified depending on your item. The value, if the value of item is less than, in our case, 25, we change the last as the midpoint -1. But if it is higher than our value, then what we do, we change the value of the index of first here by adding one more to our midpoint. So if you look at here, since 33 was not equal to 25, we did some modifications, and right now the index of lower parts, which was 0 in the previous step, now is equal to the previous middle value plus 1. So this is what we have done here.